Let's look at the general term, in the sense that let's assume that we already have evaluated the integrals up to dx small n minus 1. And then we would like to evaluate xn, the xn term. And kind of, let's first write this term. We already kind of guess, at least, that this term should be some normalization corresponding to this factor. Let's give it a name, n minus 1. And then we have e to the power I over h bar, epsilon over n, 1 over 2 m xn minus x0 over epsilon squared. So up to now, at least, the n equal to the first integral and the second integral have this pattern. So it's kind of easy to guess that the n minus first integral has this pattern. Well, we will be kind of doing, what's it called? Tüme varıma ne diyorsunuz siz? Induction. We will be doing an induction. I'm just speculating that for an arbitrary n can be 1 or 2 or 3 even. In this, n can be 2 or 3. I had already shown that this is correct. I will assume that this is true for an arbitrary n, and then I will try to show that this is correct for n plus first, and for n plus 1. Now let's evaluate this integral, dxn minus 1, dx1. We had said that, okay, the n integral, this is equal to dxn. Now from xn, the term that we didn't yet integrate is e to the power I over h bar epsilon times 1 over 2 m xn plus 1 minus xn over epsilon, all of this thing squared. This term we didn't touch before in the integrals from x1 to xn minus 1. And then we have this additional term in the exponent plus epsilon over n, 1 over 2 m xn minus x0 over epsilon squared. Times, of course, there is this normalization, n minus 1. So this is equal to the normalization term, dxn, exponent. Now let's take this, I over h bar is common, m over 2 is common. Let me take out the, if I just also take out this 1 over epsilon squares, I will have 1 over n times epsilon. Let me also take that out. What remains inside will be n times xn plus 1 minus xn squared plus xn minus x0 squared. This will be left in my exponent. I took the 1 over n epsilon out also. This is equal to, well, the normalization we have, exponent I over h bar m over 2 1 over n epsilon. We have the n times xn plus 1 squared. This doesn't depend on xn. And then we have x0 squared. These two terms do not depend on xn. Then we have n plus 1 xn squared. And then we have minus twice xn, n times xn plus 1 plus x0. These are all the terms we have in the exponent. Now we can evaluate the Gaussian integral by completing it to squareds. Okay, we have e to the power I over h bar m over 2 1 over n epsilon times n xn plus 1 squared plus x0 squared. Well, I will also take the n plus 1 out. This will be basically this term. when I take this n plus 1 out of the parentheses. And minus n times xn plus 1 plus x0 over n plus 1, all of this thing squared. And this is the term that remains when I complete to square this term and this term, those last two terms. And then I have, as a result of Gaussian integration, I have square root of pi. I'm also taking this n plus 1 out, keep that in mind. So pi 2 h bar n epsilon over I n plus 1. So if my claim is correct, then the normalization after the nth integral will be just square root of pi n epsilon 2 h bar. So here I have a minus I n plus 1 times the normalization after the n minus first integral. So kind of now we understand why we had that 4/3. You see, after the second integral we had this 4/3. This is nothing but 2 times 2 divided by 2 plus 1. 2n over 2n plus 1. I have 2n divided by n plus 1. So 4/3 now makes sense. Now let's look at the exponent. This is my normalization now. The exponent I over h bar m over 2n epsilon. And let's also take the n plus 1 out. Now 1 over n plus 1 squared out. It's this 1 over n plus 1 squared, which I took out. Now what is left? N plus 1 times n xn plus 1 squared plus x0 squared minus n xn plus 1 plus x0, all of this squared. And normalization exponent, let's simplify it a bit. M over 2n epsilon 1 over n plus 1 squared. What we have the xn plus 1 squared term. Then from the first term I have n squared plus n as a coefficient. From the second term I have minus n squared, so what is left is n. N times xn plus 1. And then from x0 squared, again from the first line I have n plus 1 x0 squared from the first term. From the second term I have minus x0 squared. I'm again left with n x0 squared. And the mixed terms, minus 2 n minus 2n x0 xn plus 1. And this n will cancel these n's. And what we will be left with is the normalization exponent I over h bar one over 2 m epsilon over n plus 1 squared times xn plus 1 minus x0 over epsilon, all of this thing squared. So we made a mistake somewhere. Yes?
I guess I've seen.
You see?
Just a brief look about.
Hold on, I think I know where I made that mistake. I didn't take that n plus 1 here. So I'm taking this n plus 1 out of this parentheses, so it should be still here, and this is what is left inside. So I forgot a factor of n plus 1, n plus 1. So this cancels one of these, so I don't have that. So basically my initial assumption was correct. And let's see, n1, no, n2. I know what n2 is. Remember, after the xn minus first integral, or I know what n1 is. After the n equals 2 gives me x1 integration, that is the n1. I had already evaluated it. This is my n1. And we had already seen how we can relate various normal factors. So this is, we can also write it as pi epsilon h bar over minus I. I forgot a factor m, I suppose, here. Yes, here I have a factor m. So it is in this exponent here. Minus I m. Then I have 2n over n plus 1 times n minus 1. So I can just repeat doing the same thing until I go to n1. Well, how many for n minus 1 I can do the same thing, etc. And eventually what I need is I have n minus 1 integrals in total. This will be, well, I can relate this to the normalization after the n minus second integral by this factor, to the n minus third integral, again by another factor, another similar factor. So I would end up having pi epsilon h bar over minus I m to the power n minus 1 times two over 2, 4 over 3, 6 over 4, twice n minus 1 over 2n. You see, after each integral, the numerator increases by 2, the denominator increases by 1. So let's see. Where? N minus 1 over 2. Yes. Because, or let's write it in this way. We have the square root of this one to the n minus first. Well, this 2 cancels this 4, and we have a factor 2. This 3 cancels this 6, we have a factor 2. And then, how many terms we have over here? No, this is not 2n, this is just n. N minus 1 terms. So this is equal to pi epsilon h bar over minus I m. Well, 2 to the n minus 1, I can just put a 4 over here under the square root. And then there is the last term, 1 over n. This whole thing to the power n minus 1. Now finally we can combine everything. This will be equal to, let's go all the way back. Now here we also have a square root, which we forgot. Because remember, that factor comes from the Gaussian integral, which contains that square root. I have this factor times square root of 4 pi epsilon h bar over minus I m to the power n minus 1 times 1 over n times the exponent. You see, we have this exponent now. Now, of course, this small n is now n minus 1. So this n plus 1 is just capital N. So let's see which cancellations we have. This m cancel this one, this I cancel this one, these cancel each other. So g of x, x prime, and t, this is equal to, well, here I have a factor of 2 pi h bar left to the power n minus 1. Then we have 2 to the power n minus 1 over 2 divided by n. Times the exponent I over h bar 1 over 2 m 1 over n epsilon x minus x prime squared. This is equal to 2 pi h bar to the power n minus 1, 2 to the n minus 1 over 2 divided by n times the exponent I m over 2 h bar t x minus x prime squared. Now I already know where this factor comes from. Remember, we had, when we take the p integrals, we have these 1 over 2 pi h bars. If you go back to our initial definition of g, these terms over there, those 2 pi h bars, those we forgot on the way. So here we have divided by 2 pi h bar. So here we have 1 over 2 pi h bar for each momentum integral. Well, we have n minus 1 of those. So we should correct our final result by dividing by 2 pi h bar to the power n minus 1. This is the correction. We had forgotten this factor. So they also cancel each other. So we don't have this 2 pi h bar to the n minus 1. So that is one correction. Now that 1 over n, let's see how many factors of momentum do we have. I was kind of lousy about my overall factors. how many x insertions did we do? We inserted n minus 1x, right? How many momentums did we insert? For each xi in the bra, we inserted one momentum, right? So we basically inserted n of them. Do you agree? So we have n momentum insertions. Each one of these momentum integrals brought this factor. So probably I was right when I said this was n over 2, not n minus 1. So this is n. But that basically means I have one more such factor. Oops. So this is another correction. Because we have only n minus 1 xi insertions, whereas n pi insertions. Now let me just check one thing more. Now all of this factor is also under the square root, right? So this is not just 1 over n, this is square root of n. So this is square root of n. So this is not 4 pi, this is just 2 pi. It's already under the square root. So I don't have this factor 2. It's just 1 over square root of n. 1 over square root of n. So we have the final result. X prime t. This is equal to square root of 2m pi h bar over I times t, because epsilon times n is t, times exponential I m over 2h bar t x minus x prime squared. And if you remember our previous expression for the free particle, I mean, if we didn't miss any other factors of 2 or pi, etc., this was the result we had. And at least I remember that we had this 1 over square root of t, and we had the exponent with x minus xi squared over t. If you remember, we had said that it's basically a Gaussian. In imaginary time, it's a Gaussian. Well, of course, you can think that, well, we could solve this easier with or already known wave functions, etc. Why bother with all these long calculations? You are asking it, right? He is. So, I mean, one advantage of this path integral let's look at this one. No, even let's go this one. So this was our initial expression. Let's go to imaginary time. Remember, we had this operator over here, and then when we said t is equal to minus I h bar beta, we just recovered classical mechanics. So this just becomes e to the power minus beta t. Now beta h, where beta you can identify with 1 over the Boltzmann constant times t. Well, this is also nice computationally, because in numerical calculations, the integrating oscillating functions is kind of more difficult than integrating exponential functions, exponential decaying functions. We can calculate exponentially decaying functions more reliably. So this limit is also nice in that respect. But if you make this transformation, gx prime xt becomes, or beta. Well, we also make the same transformation in epsilon. So it just becomes 2, let's just say some normalization, whatever you choose, times the integral over dxi. Well, you are going to imaginary time, let's say, or so e to the power minus e over h bar 1 over 2 m dx by d beta squared, or let's say dx by d tau squared plus v of x. You will be integrating over tau from 0 to beta. Now these xi, there are a finite number of them. Tau integral is a continuous integral, but you can just discretize it. So for a given path, you can easily evaluate your integrand numerically. Well, furthermore, it's a finite integral. You don't even need to go to infinite integral with infinite range. But we also said that this we can also write is not as an integral over the xi's, but just as a summation over all possible paths. So we can just find the paths that have the most contribution. So you can just, this is our energy functional. So for a given path, you can calculate the energy functional. So numerically, then the next thing to do, you just change your path slightly. If it gives you a lower energy, just keep the new path. If it gets a higher energy, just take that path with a given chosen probability, let's say. And then you can just consider many such paths. You start with an initial path. Let's say this is our lattice. So we will also discretize time, or in this case it will be tau. We have a finite number of points. Let's say you should start from here and end over here. This is x prime, this is x. And then what would you like? If you take the free particle as an example, this is the classical path we already know. Well, you can imagine more complicated problems where you don't know the classical path explicitly. But you can just start from a trial function. This is a trial function. You calculate the energy functional for that trial. And then you have, let's say, E0. Then you pick one point. You can pick one point and change its value. You can say that, okay, let's put this on the lattice. So the x also can take discrete values. Let's say you take this value and change it to this one. The other ones will be the same. So you have E x, let's say 1, the first modification. You evaluate the energy of that one, let's say you obtain x1, E1. If E1 is less than E0, then keep the path. If E1 is larger than E0, then keep the path with probability e to power minus beta E1 minus E0. You just pick up number. If that number is smaller, you pick up a random number. If that random number is smaller than this one, you still keep the path. If it's larger than this one, you don't keep the path. You just repeat it like this. You just choose this point afterwards, change it to this value, and then you have a third path. Repeat. To obtain m different paths. And in principle, you should choose m large enough. So in the ideal case, it will be infinite, but on a computer, you can just choose m to be large enough. But then you will have a distribution of paths. So the paths that have a small energy, you will have more of them, and paths that have a larger energy, you will have less of them. Then let's say, suppose you want to calculate, what do you want to calculate? You are collecting paths. You will have at the end m of them. You are changing the path, but each new path, if it is lowering the energy, you are taking it. If it is increasing the energy, then you are ignoring it and taking it with a given probability. So you are making your collection of paths. Then let's say you want to calculate, what would you like to calculate? Let's say the energy of the ground state. Now let's look at this one. You might not know the ground state, but let's say you want to calculate the energy of the ground state. Well, you can do the same thing for all of these paths that you like. So this will be just a path integral. You can just repeat what we had done before. Path integral of e to power I over h bar s x. No, we are now in the imaginary time, so it's minus 1 over h bar e. So here you will get e of x and p. So this will be proportional to this one. Just repeat what we had done before. But now we already have these paths. What we have to do is just write this as sum over all paths, or the average, sum over all path of evaluate the energy of that path times e to power minus 1 over h bar e of the given path. divided by the total number of paths. So this is basically the definition. It's the path integral. Let's just divide this by x. This is suitable normalization. Now what we did here, we already had created this ensemble of paths. So the paths that have a large energy, we have very few of them already. And the paths that have a small energy, we have a large number of them. So this exponential factor over here, what it does is it just suppresses the contributions of the path with high energy relative to the contribution of the path of lower energy. But when we were all... No, you see, here, in this expression, it's sum over all paths that you can mathematically imagine, not among the ones that we have selected, but over all the paths. But the advantage of the paths that we had already taken is that they have already, the number of paths that have a high energy is already suppressed. So we don't need to double suppress it. So we just sum over all the paths in our ensemble now, here, in the last line. Now, okay, this is probably not so rigorous definition of what is called importance sampling. You just select a group of paths and you choose paths that are more important with a larger weight, basically. Now, of course, for the free particle, this doesn't really make too much sense, but let's just imagine you have a theory like the quantum chromodynamics, which we don't have a solution. Analytically, we cannot solve it. But still, this method just scales proportion. I mean, you can scale it to any complicated problem. What you need to do, the algorithm that you need to write, is more or less identical. So in that sense, in that case, especially the path integral becomes much more important, much more interesting, let's say. And this is called, for quantum chromodynamics, let's say, at least, it's called the lattice QCD. Now, there are a couple of more things that I would like to discuss, but we will discuss it on Sunday. And at least one thing I would like to discuss is, what about perturbations? So let's say we have this G, which we wrote this as Vx e to the power I over h bar integral dt from 0 to t 1 over 2 m x dot squared, let's say minus v0 of x minus lambda v perturbation x at t. Or let me just add minus v of x at t. Let me also add this product. Now, if this wasn't an integral over the x, what we could have done is, in wherever we have this x of t, we could have just replaced it with the derivative with respect to lambda of t, lambda. If there was no integral over there, any appearance of x, we can replace it with taking derivative with respect to lambda, because derivative with respect to lambda would just bring a factor minus I over h bar x. just mathematical tricks that we use also for calculating some Gaussian integrals. Well, here there is an integral, and so lambda is not just a number, but it's a function. So what we invent are functional integrals. If you have some function f of t, and if you are differentiating it with respect to f of t prime, we just define this to be Dirac delta t minus t prime. Now, why is this definition? If you take the discrete limit, remember what our x of t was. It's just like xi. And at a different t prime, xj. These were just ordinary numbers. And if you would take the derivative of xi with respect to xj, you would get Kronecker delta. It will be 1 if I and j are equal, and it will be 0 if I and j are different. Kronecker delta ij. But remember, we had defined the x of t to be xi, where t was epsilon times I. So if you just take the limit that epsilon goes to 0, Kronecker delta just becomes the Dirac delta. Now this xi is nothing but x of t, or f of t, and xj is nothing but x of t prime. Well, the nice thing about this thing is that, for example, if you have such an integral, if you differentiate it with respect to, let's say, lambda t prime, this is just x of t prime. And g of x prime t would be just dx e to power I over h bar dt 1 over 2 m x dot squared minus lambda x all of this thing multiplied by e to power minus I over h bar dt, the potential, but this time evaluated at h bar over I, the derivative with respect to lambda t. So if you can evaluate this thing with an arbitrary lambda, well, that is for the free particle, it will be kind of trivial. Well, trivial meaning that we have to follow all the previous procedure. Well, there are easier ways. And then we can just expand this up to an arbitrary power that you are interested in the potential. So you can have all those corrections that you are interested in. Corrections to the energies, correction to the wave functions, etc. But that we will pick up on Sunday. Well, there's also the harmonic oscillator that can be solved. Oh, okay. Well, you see, when you write anything in terms of the paths, things start to get easier. You can split your paths to paths that go above your magnetic region of magnetic field and paths that go below your region of magnetic field. So both of them will acquire, all the paths that go above will acquire a given phase. All the paths that go below will acquire a different phase. So the phase difference will depend on the magnetic field. Well, we will also do that, okay. Well, I mean, it's, again, and repeat, it's boring to watch it, the derivations. You should do it on your own. Now, also for the harmonic oscillator, you can evaluate it. It becomes interesting how you see the ground state energy, at least. That's kind of easy to see. Or even the energies of the excitations, because they just appear as the poles in the Fourier transform. So you just need to find this G, evaluate its Fourier transform, and see where the poles are. And they will give you the ground state, all the energies of the excited states. And then you can try to calculate, I don't know, the wave function of the ground state. Because that is nothing but the residue at the pole. Any last minute questions? So see you on Sunday.